we have G is Poincaré, so it is SO I S13. Let me take it in a 4 dimension, right? Since I'm looking for application to 4-dimensional gravity, of course. Right, so it is H semi-direct R4, like this. The symmetry, therefore, of the underlying boundary is local Lorentz, right? Again, no gauging of translation. And we can write, therefore, an element of this or this we can write in a matrix form like this. Let me write S 0, 0, 1, 0, translation 1, like this. And let's say that an element there will be written like this, right, at the matrix form, so only valued in the Lorentz piece. So this is a group element. The group element is a function with value in the S13, and therefore we have the Cartan connection, right, like this. Very easy to find, and the Cartan curvature will therefore be written as yes, okay, split, yes, okay, splits as R and theta. It is very easy, simple matrix calculation, right? Shows you that it is just 1 half omega, and here it is E plus omega E. Easy.
The first line, SO what?
SO13, yes, sorry, SO13, the Lorentz group. Yeah. Well, of course, sorry, I should have started with that, of course. So, A, the local version is this. Alright, so we can call F like this. Should I call it F maybe? Okay. We can call it R and T. Okay, those are the local version through some section like this. And in a normal case, as you all know, so the normal Cartan connection, so the normality conditions are imposed on the curvature because we want them to be gauge invariant. If you think in a physical way, so we put torsion equal to 0. This allows to express omega, the Ereshman part, the Lie-H part of the Cartan connection in terms of the solving part. So indeed, in the end, it means that omega n is in, sorry, yeah, in terms of theta, I should write probably here, something like that. And here it means that we have E theta 0, like this. And so this normal Cartan connection, this one, indeed represents the degrees of freedom of gravity in the vacuum. Of course, we have eta R4, the Minkowski metric, right? We can give us, will induce, as we've shown in the general situation, will induce a metric G eta E on M, and therefore we have a Hodge. Why not? You can use it to do Young Mills. But we don't need it to do gravity. And as to the gauge, well, okay, I could say what about the gauge transformation, but it's clear, right? You use this matrix, you know. So gauge transformation. Right, so you use this matrix and this form of the connection, and you compute this explicitly, easy. And same for the curvature. Right, so all your gauge transformation are given like this in terms of the Lorentz parameter gamma. The linearization is obvious. And as to the Lagrangian, so this is again the kinematics, basically. Now the dynamics. Lagrangian of GR plus cosmological constant, positive cosmological constant, right? So it will be written like this. So it should be a four form built from A bar, so A and E, or rather, so since we want something tensorial, we will use tensorial form. What are the tensorial form here? Well, the curvature, of course, is, and the soldering part is too. Right? So we have at least 3 candidates to build a Lagrangian. The most obvious thing we can write is something like this. E transpose, right? So this is vector valued and line valued. This is a matrix. This is a matrix also. What I mean by this is actually this AB. So sorry, I should have written slightly differently. Eta minus 1 E transpose like this, and explicitly this notation means R AB. So this is the Lorentz index of the two form R, right? E A B epsilon A B C D. So you consider the epsilon, the Levi-Civita symbol, as a polynomial, that pairs object, matrix valued object like this. So this is symmetric and well defined for Lorentz valued object, and it is Lorentz invariant. So it is invariant under. So this polynomial is indeed invariant under the action of that guy. So we satisfy the local Lorentz gauge principle, right? Very fine. So the good theory. And another term that you can write, so let me, sorry, I've been a bit ahead of myself. And another term that we can write, that we will write, is the cosmological constant term, which is basically just the volume of space-time, so it's a volume form. So we write something like this. And so this is, so E, A, E, B, E, C, E, D. Everyone, epsilon A, B, C, D. And again, this is perfectly Lorentz invariant, because this combination is a tensorial object still. So here is the Lagrangian. From the Lagrangian, we extract the field equation easily. Right? So sorry, I will remove this like that. So variation with respect to a bar of L. So let me call it Einstein-Cartan. Einstein-Cartan Lagrangian here. So it is exactly like Einstein-Hilbert, but written in the Cartan language. So we will have Einstein-Cartan field equation plus wave potential. Ah, sorry, I have a clash of notation. So, well, okay, not fine. Not locally, not on M. Right? This soldering live on P, the Lagrangian live on M, so no clash. Okay. This is the pre-symplectic potential as well. So, right, so this is E of delta A bar plus D of theta delta A bar, like this. And so, what are those? So, yes, so the field equation, Einstein-Cartan 2, like this. So, delta A splits in two nice pieces, like this. So we have two linearly independent field equations. The first along delta E, right? So we have something like that. Delta E, no, sorry. And yeah, we have something like yes, is under 3 E transpose like this. So this is the first equation that we have, plus delta A, and then we have T. Sorry, yes, T. So those are our two field equations. And you have the boundary term, theta, which is simply delta A E dt. Okay. So what is interesting is that this piece is Einstein equation. This gives you the Einstein equation. If you unfold the combinatories with the epsilon, this will give you the Einstein equation with the positive cosmological constants. very fine. And this will give you, well, torsion 0, because this should be on shell, remember? So I should have written maybe like this. So E, so requiring E equals 0, give us, so change color. So this is equals 0 then Einstein equation, and this gives us the t equals 0 condition, which in this case means give us that the Cartan connection is a normal Cartan connection. Okay. So again, the Cartan connection encodes the vacuum degrees of freedom of gravity. So in that precise case, the normality condition arises from the Lagrangian. It is not imposed on the kinematic level. Now about the charge, remember we had that from this guy, this boundary term, we could extract the charge by some metal thing. So charge. Charge. What is the charge in this case? So maybe you remember that it depends. Let me call again chi in the Lie algebra also 1, 3. So that's the Lie algebra of that guy, right? In matrix form, it would be a chi 0, but we have dimension 1 and for sigma equal dimension 1 submanifold, we have that the charge in the Einstein-Cartan setting that depend on the Cartan connection should be written as we would do in the Yang-Mills case. We simply plug in. First we integrate over sigma. The variation, so the infinitesimal gauge variation of the connection. So we would have d chi e. That would be the definition of the charge in that context. But we see that we can do something. Yeah. We can integrate bypass that term and get that we have a boundary term like this plus something that will essentially reproduce chi up to some coefficient which I don't care about, et, but dE is the torsion, right? And on shell this is 0. So again we see that. So on shell this is 0 for the normal Cartan connection. Therefore, the charge is again a boundary term. Well, different boundary term as we would expect from general consideration, but okay, this is a boundary term. One issue that we have here, nonetheless, is that remark. So the homogeneous space of the theory at the kinematical level is simply Minkowski. Right? Is therefore with this, so Minkowski. This. But when we look at the charge here, we see that this charge is non-zero. Is never 0, even on Minkowski space. Right? Because even in Minkowski space, there is no reason this to be 0. So, or say otherwise, if you want to think in another way, if you have an isolated gravitational system, like I don't know, the Churchill solution, the black hole or whatever, and you would look and you would push asymptotically the boundary super far, you expect to be asymptotically onto Minkowski, on the flat model where the gravitational field is weak, and you would expect that therefore this charge will not vanish. No, scrap that. Okay, just this is the important piece. Right. So it seems there is a kind of clash, which is Minkowski, blah, blah, and Minkowski, yes, indeed. N plus. So that's the first remark. And the second remark is that can be traced back to another remark, which is that the ground state of the theory is not the homogeneous space of the geometry. Right? The homogeneous space of the geometry again is Minkowski. He's there. He's that guy. But the ground state of the theory, given the presence of a Cauchy constant, will be the Sitter space. Ground state of the theory is ADS. ADS 4. Right. And so probably the clash or the issue, but so the issue may come from here, and so there is a way, as I explained before. When was it? Okay, yes, there. That we may try to align, to match the theory with the geometry. It seemed that okay, we took a, so to speak, a wrong kinematics for the theory that we wanted to write. Right? So let's try another one, another Cartan geometry. The Sitter. Since we have the ground state which is the Sitter, and see how it goes. So in the De Sitter case, it's almost the same. It's not changing. I think I will finish with this example. So let's see at Cartan de Sitter. So in this case, G is O. So let me take the positive. Okay, I did already. Positive cosmological constant. So this will be my group SO14. The local group of the geometry will remain the same, right? This is it. And G over H is the Sitter space. Very good. The Cartan connection is now, okay, let me take the local one immediately, is like this. Let me take the coefficient immediately perhaps. Well, okay, it will be just bothering. So this is L, and this is minus epsilon L E 0. We have that the curvature now, if you again use the Cartan structure equation, you easily see that you will have R minus epsilon L squared. What is it? Here, E, and here we will have E over L, DE plus AE, 0, 0, very fine. So this is the Cartan connection, this is the curvature. Good. And the Lagrangian that we write will be slightly different than that one. So we will call it the McDowell-Mansouri Lagrangian. So how it is defined? Again, you would like to satisfy a local Lorentz symmetry principle. Look at the kinematics, what it is given. Well, you have the torsion, you have the, I can call this, let me call that guy F for short. Right, so again a tensor object, and this is T of course. Again, torsion. Again, in the case of the normal situation, this would be 0, right, easily. So A would be AE, right, this. And so you want to write a Lagrangian, you have 1, 2, 3 candidates as tensorial form. Well, again, the most obvious thing you could write, modeling a bit that guy, would be a Yang-Mills type Lagrangian, which you need to take F, like this, that is F, A, B, F, C, D, epsilon, A, B, C, D, right, something like that. folding F, what you get is R minus, and now let me be precise. Epsilon over L2 of, well, epsilon over L2 of exactly that term. Right. So this new Lagrangian corrects the Einstein-Cartan Lagrangian with the Euler characteristic of the base manifold. Right. So this is a topological term. It will not change the field equation. Right. It can only change the boundary term. So the symplectic potential. Right. So this is Euler. So this is a topological term. Therefore, do not change the field equation, basically. So let's see, for example, let me give it anyway. So Mansury, delta A, this is delta E. So up to the coefficient, it's over L2 maybe, of F, like this, plus delta A, again T, like this, and the boundary term, theta Mansury, from which we extract the charge at the end, okay, is something like, well, it's easy, it's just delta A F, like this. So it's otherwise it is theta H in Cartan plus theta Euler, if you like, so to speak. Right. This will be the boundary term coming from the variation along A of the Euler term. It will only be something like this. So it's a correction of the Einstein-Cartan Lagrangian charge, and so now the charge now, Mansury, is simply given by integral of, so the same would be dE, where is it? Sorry, yes. d chi f, and on shell we will have that it is dE of chi f like that. And again, this is on shell. This is on shell E0. And now this is a much better charge because indeed we see that on the homogeneous model, on ADS, this is the ADS curvature F. On the homogeneous model, this is 0, right? And so the charge is 0 too. So now the homogeneous model gives you a good zero reference for mass, energy, angular momentum. Yeah. So that's good. So equals 0 on. So this is a good point. So this theory is better, so to speak, at least from the charge and symplectic point of view, than the more original from the original one. Right? Yeah. Fine. And in the maybe 5 minutes? Yes. Yes. Something like that. 5 minutes. Okay. So I'm pacing through the example quite quickly, but it is just to give you a sense of how these unfold quite naturally. Once you start from the geometry, you have a quite obvious choice of Lagrangian to be made. Easy to derive the field equation, easy to derive the charge. So yeah, and it's smart to align the geometry with the Lagrangian you want to write, because indeed these, in a sense, this parameter in the original theory you wanted to make was not naturally here. Sorry, I forgot to write that. Indeed, you can identify now. Okay, given this, you can identify the fact that L. So, if you want to make the matching between these and these, you identify, sorry, 1 over L2 with lambda over 3. So in the sense, this parameter was not natural with respect to the original Cartan geometry, but you were free to add anything that was tensorial. This was just a kind of a proportionality term. You were free to make it, but it appeared in your field equation, giving you a ground state for your theory that was not the homogeneous model. Now, starting from the Sitter geometry, you have naturally a parameter with a dimension of a length, or you could naturally introduce it. And therefore, when you write your object, you naturally identify these fundamental scale in your theory with the cosmological constant parameter that you had before. Right? So again, it kind of makes sense to choose the right geometry for that. And just to say a word about the conformal situation. So this, of course, is the model that is most empirically adequate. Right? This is GR. But still, in physics, we like to do to search for possible generalization, and conformal gravity has been a case of interest, right? If only because conformal symmetry in general is something interesting. So, conformal Cartan. Conformal geometry. So in this case, again, I will relate myself to the 4-dimensional case. So G in this case is SO to 4. H is the symmetric product of SO 1, 3 and R 4 dual. In matrix form, I will write something like I will write, let me call it Z S Z minus 1 0 0 0 0 0 0. I have to write matrices, and so this is Lorentz, this is the virus scaling, right? And this matrix is 1, let me call it L, 1 over L, sorry, 1 matrix 0 0. Right, okay? So this is how you will write your group. You can write your group like this. The homogeneous space G over H is the conformally compactified Minkowski space. That's what we told us about. And of course, the Cartan connection will split as, let me call it A, B, 0, E, A, 0, P transpose, minus A, and accordingly the curvature. Again, I'm just dealing with the local guy here. Torsion 0, torsion 0, Cartan transpose minus F, right? And the normal Cartan connection in this context will set the normality condition in that conformal context will set to 0 a bunch of components of the curvature, also requiring that W A B A C equals 0. So the Ricci contraction of the Lorentz piece is vanishing, right? There is also probably a choice of gauge that should be imposed here to arrive at this result, say, which is that loss of generality. And so this would give you the normal situation. And doing this, again, implies that, so those various conditions imply first that A equal A of E and P depends on A, right? Therefore on E in the end. So again, in that situation, normality condition will imply that simply, indeed, the Cartan connection in the end only depends on the soldering part. Right. Now, if you look at how the gauge transformation work in that situation, you will see what I have hinted at in the general case, which is that you will induce a conformal class of metric. Why? Because if you look at A gamma, right? So gamma now takes let me call it gamma 0, say, that guy. Okay? If you just look at, for example, how, okay, gamma is like this. So gamma will be again an element of the full group. And this would be gamma 0 and gamma 1. If you look at this and look at how the soldering part is transformed, you will have that this is Z minus 1 S E, and okay, I don't care what happens everywhere else, right? So if you have eta on R4 as before, and I finish soon, you see that the metric that you would want to build, if you transform it, right? So G gamma, so to speak, by means of writing this, the gamma. This will give you simply Z2, Z like this. This will give you Z2. So the gauge group of the bundle acting on the Cartan connection will induce a conformal class of metric through that by that means. That's the kinematics. And if you want to write a Lagrangian, so conformal like this, again, what would you write? Well, something nice, obviously, again, of Young-Mills type. So you have this big, nice tensorial object. So let's try to write something, and you have a metric. So why not write something like this? Sorry. Right? This is quite complicated, many terms. If you restrict to the normal geometry, like this, then what you end up with in the end is just trace of W. This is the Weil tensor, and this is called Weil gravity. Right? It depends only on E, because in the normal case, A depends also on E only. So this is Weil gravity. And what is fun here is that Weil gravity written like this, if you want to find the field equation, this is quite complicated because, okay, W as a function of E is elaborated, so it's quite a lot of work, but from this perspective it's very easy because you know how to get the field equation. This is Young-Mills type Lagrangian.
You have one more minute.
Yeah, and I'm finished. Perfect. I think it's perfectly good. So the field equation are simply exactly like in the Young-Mills case, something like that. Right? So in the end, the equation is of Young-Mills character, right? And again, limiting to the normal case. So let me call it normal 2 here, because there is the connection. And this is exactly, so the field equation here has been, of course, worked out. It is called the bar equation. The bar equation, kind of a lot of work to be done there. But here it is very easy, and it is therefore conceptually natural to see that the bar equation is encoded into the Young-Mills equation from the normal conformal Cartan connection. This has been proven in 2003, from just starting from some parametrization of the Cartan connection, and this side has been demonstrated in 2003, but this is obvious when you use the full Cartan conformal situation. Okay, thank you.
So, no questions. We have 5 minutes break.
Yeah,
questions,
exactly.
if you like personally. I have also questions if you like personally.
Nothing.
Okay, so we start in